Bismillahirrahmanirrahim. Today we'll be discussing cognitive science and also looking into inductive reasoning. Now, the most basic definition of inductive reasoning is the gathering of information, intel, discerning, analyzing, utilizing a rigorous methodology or a set of methods that eventually lead you to a general conclusive idea. So, for example, the sky is blue. The inductive way of approaching this is to start from point A. Point A is the point from where you understand what sky is, what color is, the spectrum, the wavelengths, matter, which is your solid, liquid, gas, plasma, and the atmosphere, stratosphere, so on and so forth. So understanding all of these things are crucial in that particular scenario. So do a quick Google here. Inductive reasoning logical process of specific observation data analyzed to form broader generalization theories. It is essentially bottom-up approach to logic rather than starting with a proven rule. You look for patterns in evidence to build a probable conclusion. Yeah, perfect. Right, so I've devised a prompt here for the Gemini LLM. So for those who want to, for example, look into the research of different and various papers, you can easily do so, right? So the prompt is, I'm going to paste papers that outline neuroscience, cognitive science, and other scientific research, because we have some behavior stuff here as well. For each paper, I will paste links and or DOI numbers. I need you to act as a professor and a seasoned academic. Tell me in a paragraph or two aim of the study, methods employed, what was found, and main findings and limitations. So I've pasted a paper here by Hull from the 20s, which we'll explore in a moment. So the text I'll be using today is Thinking, Problem Solving, Cognition by Richard Meyer. And this is a key text for anyone looking to jump into cognitive science, or AI, or cognitive neuroscience, even behavior psychology is very important actually. So this is a great text, and credit is due. So concept formation task. So he opens up this chapter number 4, with a concept formation task. So point number 1. Okay. Suppose you have in front of you a pile of cards with different pictures of different colors, shapes, sizes, number of objects. The colors are red or green, shapes are circle or square, the sizes are small or large, and the number of object is 1 or 2. So some symbolism going on here. The experimenter picks out one card and places it in one of 2 boxes. Box yes or box no. Each time the experimenter picks out a card, you must guess which box it belongs to. The cards and their group, yes or no, are shown in box 4-1, which is here. Okay. Cover the column marked correct group. So it's asking us to cover, which we will do here for now. Okay. And try to guess the group membership for each card, and then check the correct answer and go on. See how long it takes you to predict group membership without error. So states here that you will be given a series of stimuli individually with each item varying in shape, circle or square, size large or small, color red or green, number 1 or 2. Cover the column, which I have, and label correct group with a folded piece of paper. Each item listed on the left. Guess its group, either group yes or group no, then slide the folded paper down 1 notch to check if those is correct and so on. So okay, I think I know where this is going. Let's carry on because this makes no sense. Okay. In another example of this kind, an experimenter enters a room, points down to the metal legs of a table and says "Ugo," then goes to a wooden chair, says "Ego." Having accomplished these two scientific tasks, he moves towards a door, points down to the metal doorknob, and again utters "Ugo." Next, he points up to the top half of the wooden door and says "Ego." Suppose you were in a classroom experiencing all of this. Now you might be sitting a little higher in your seat with your eyes brightening up a bit when the experimenter points to the spout of a water fountain. What response do you suppose fills the room? A chorus of "Oogle," you say. Experimenter smiles and replies, "No, it's an eagle." So these are just made up words so far. Okay. The process of pointing to things and telling to which category they belong continues until people in the room are getting long runs of correct anticipations. So it's the anticipatory behavior that's being observed here at the same time, along with category confirmation. Okay. The process of pointing to things and telling to which category they belong continues until the people in the room are getting long runs of correct anticipations. The rule the subjects later report is based on which the experimenter's finger points. If it points up, the object is an ugo. If it points down, the object is an ego. Okay. Consider another example. Now, this might sound ridiculous, but this is how categorization is worked, even with this absurd example. But here's another one. Young Billy is looking out the window and sees a poodle. Mother points to the poodle and says dog. Then a German shepherd walks by, and again Mum points and says dog. Next, a terrier wanders down the street, and Mum says dog. Then Billy is beginning to catch on. So when a new creature strolls into he jumps up and down wildly, pointing to the little animal, shouting dog. However, this time his mum says, "No, Billy, that's a cat." What's interesting in this example is connectionism, specifically distributed connectionism, can explain why this confusion occurs. Right? Because four-legged animal, furry tail, moves on all fours. That's why the child, in this case Billy, seems to be confused. But that's not our topic for now. All these examples of concept learning are examples of concept learning because the subject, the person, must learn a rule for classifying objects into mutually exclusive categories. In general, each particular presentation of a to be classified stimulus is called a trial or instance. For example, one red large circle is the first instance of a no category. Each instance may have several dimensions: your number, color, size, and so on. So this is similar to over the past few months, I've been discussing the Wisconsin card sorting task, and it's a very famous cognitive task, and it has a set of cards, and these set of cards are utilized trial by trial for the participant to identify the correct rule, which could be matching the color, matching the number, matching the shape, so on and so forth, even position as well. And each may have and each dimension may have several possible values or features such as red or green, large or small, and so on. So yeah, so you have a trial. So concept learning is the act of classifying objects into mutually exclusive, meaning they are independent categories. And participant has to observe the stimuli, right, and classify this stimuli, i.e., this action is a trial, right? This occurrence is a trial, and each instance has several dimensions, right? So number, color, size, and so on. So these are dimensional because numbers have predictive power, so dimensions can be changed, right? And number similar to color and size, because color and size determines the accuracy of a dimension to a degree, right? So, and within each dimension, there are several possible values or features. So, for example, red, green color, so these are features and what gives it value. For example, the color gold, by virtue of the element gold, has more value than silver. If it was switched around, the values will be inversed in this particular case, in that example. Now you have large or small size. So size again is dimensional, but it's incongruent. It acts in harmony with features. Because if there's a feature of a car, for example, this car can go from 0 to 60 miles an hour in 5 seconds. That number, which is telling me that this car has a feature of being very fast, right? The acceleration is very fast on this car. That feature then lets me classify the dimension within where this car sits. So that dimension could be sports car, hypercar, elite car, so on and so forth. So this is typically inductive reasoning, where first of all you have to verify concept that you're working with, and can this concept be put in a trial and be used as an example or a trial or an instance, right? That is very important because if a trial cannot be utilized, i.e., a workable model is not identifiable, then it's just a waste of time overall. So it's very important when it comes to inductive reasoning that you have all the data and analysis ready that can be applied onto a workable model, simply put. These examples illustrate two main types of concept learning tasks. When all the basic stimulus dimensions are described in advance to the subject, who must then identify the relevant rule. So there's two main types of concept learning tasks, okay? when all the basic stimulus dimensions are described in advance to the subject. So dimension is what? Number, color, size. For example, these three dimensions, once they are described to the participant, okay, in advance, and then they must identify a relevant rule. There must be a rule that corresponds with the trial that they are partaking in. This type of concept is called concept identification. Very important. In fact, I'm going to put an extra emphasis here. In the first example, for instance, you were told all the dimensions such as red versus green color, large versus small shape, and so on. When the subject does not know the basic set of potentially important stimulus dimensions and must develop or produce it in addition to identifying the relevant rule, the task is called concept formation. Right? Nice and easy. I'll repeat that again. When the subject does not know the basic set of potentially important stimulus dimensions and must develop or produce it, so has no idea, but now is attempting to identify and formulate. In addition to identifying the relevant rule, the task is called concept formation. So this is where a concept is being formed now. It's hard to pinpoint a dimension, and because of that, it's hard to discriminate and understand that the features and characteristics involved of said dimensions, respective dimensions. So it becomes a big challenge actually. The Ugle-Eagle problem, in which you were not told the dimensions, included wood versus metal, up versus down finger, and so on, is an example of that kind of concept learning. Note that when people try to solve problems like these, they sometimes begin by forming rules or hypotheses that are based on the wrong or too few dimensions. For example, small, yes. Metal, Ugle, animal, dog. But as more experience is acquired, correct performance increases. Ah, interesting. This is where my actually thesis is semi loosely related, because what I am looking at is the errors that occur temporally during the Wisconsin card sorting task. And the errors can be due to attentional drift. This could be due to preservative errors or set loss errors. These are different errors that occur during decision making and the cognitive tasks. So I'm analyzing why performance drops dramatically and how certain after a certain number, X number of trials, the rule is dropped or the rule is forgotten or the rule is replaced entirely. Right. So my supervisor and I, Professor Cooper, he had done great work in this back in 2023, and we looked at the Bishara model from 2010. And the mathematics behind Bishara is, for me at least, new, fairly complex, but alhamdulillah, I got the hang of it. So here we, so there he looks to identify three separate categories: attentional drift, preservative errors, set loss errors, or attentional shift. They are to a degree interchangeable, but let's say attentional shift. Okay, so these three categories is what's being looked at in the Bishara model in 2010. So the remainder of the chapter will investigate the thinking process that underlines this improvement. Right, so this is the aim of the chapter. Rule induction definition of thinking. Okay, so hopefully this makes sense. Yeah. Right, so The concept learning example provides a basis for a theory of thinking that go beyond the simple response hierarchy model. The thinking process required in concept learning has been characterized in a number of ways, including two classes of theories. So there's two theories when it comes to concept learning. Okay, so I think it's important that we highlight this. So number one is the continuity theory, and the other one is the non-continuity theory. Let's see what's going on here. So, the continuity theory views concept learning as a direct extension of SR, which is stimulus response associationist model. So this, in a simpler term, states that stimulus evokes a particular response, and that is the case every single time. However, I'm not trying to change this into a statistics debate, but if you're a frequentist, that might be held true, or if you take a Bayesian approach, it may not be the case. It's similar to the black swan problem. Every day you go to the lake and you see a white swan, but by happen chance there's a black swan. Therefore, there's a possibility that there are swans of other colors, right? It's a very reductive sort of example I've given here for the sake of this string. But yeah, that's where we at least get a glimpse of maybe there is a limitation within the associationist model. So each feature of an instance serves as a stimulus, and the particular response is strengthened for all presented features on each trial. So what's interesting is the strength of a feature. This can be incremental or this can be all of a sudden. Now, I'm going to use this example a lot, but going back to the Wisconsin card sorting task, we don't dramatically increase the strength of said features, but they do catch the participant out. And this is where, for example, we see a drop in performance when the number rule changes or when the shape rule changes, where one has to make a direct association. Again, this corresponds with the continuity model, theory, sorry, that if two red triangles are given to you on the card you have, and then the set that's presented, you have two different shapes, yet you have the color red with two squares, but you have two blue triangles. So which way do you go here? And to throw the participant off, usually the shape of the triangles are different. So, and for example, if they have two equilateral red triangles, we will present an equilateral triangle and an isosceles triangle, whilst the square would be equally sided and it will be two and it will be filled with the color red. So there seems to be a continuity in that particular instance that, okay, two equilateral triangles must match with two equilateral squares. Colors are red. In the center of the card that I have and the center of this card that's presented, can't be the triangles, it can't be the circles, it can't be the plus sign, it can't be anything else. So this decision making is what Reddish appropriately puts as procedural decision making, right? Where the basal ganglia and the hippocampus, of course, play a vital role, and obviously, without doubt, the prefrontal cortex, right? Now, how these knowledge structures are formed and everything else, it's not our concern right now. But what is interesting is there seems to be a difference when it comes to the acquiring of such knowledge through the Wisconsin card sorting task. So, interestingly, a paper by Braver from 2009, I believe, which was quoted by another researcher, O'Neill or O'Reilly. I think it's O'Reilly or O'Neill, one of the two. Quotes this that dopamine actually plays a big role when it comes to this. So as you can see, there's a multifactorial process going on here when it comes to decision making. Anyway, so particular response is strengthened for all presented features on each trial. Thus, after many instances are presented, only the relevant features will have consistent and therefore strong responses associated with them. Thinking is simply building response hierarchies. Okay. Non-continuity theory views concept learning as inducing role or hypotheses and testing them. If the rule can predict class membership for any instance, it is retained. But if it cannot predict class membership, a new hypothesis is generated. Thinking is hypothesis testing. So this is the key difference here. Continuity theory, thinking is simply building response hierarchies. Okay, what can be, might be, what could be, can be, and then pick the best one. That's continuous. Non-continuity theory suggests that thinking is hypothesis testing. It's constantly trial and error, trial and error. The continuity of the continuity or stimulus response associationist view and the non-continuity or hypothesis testing view yield different predictions about subject behavior, which the next two sections of this chapter will investigate in more detail. There's the subject's behavior that's being observed here. Excuse me. Just trying to see what examples they are using here. Okay, Reno. Okay, Posner. Okay, they've used visual theorists. Okay, lovely. Inducing scientific experiment. Mm, mm, okay, very nice. Okay, okay. This is this chapter is a nice outline of what we're looking to achieve here. Okay, so continuity theory. We're gonna begin with this. Okay, use this color. The most obvious and straightforward theory of thinking is that the concept learning task is a simple extension of the response or habit hierarchy described in chapter 2. What was described in chapter 2, I will very quickly show you here. It's similar to this cat experiment. You can view it on page number 23. There's a hierarchy of decisions. The one that yields the most perfect response or matches with expectation, even if the expectation is not there to begin with, it gives color, right, to your uncertainty. That is the ultimate decision. During concept learning, the subject forms a response hierarchy for each attribute in the problem by tallying the number of times each category response has been or has not been associated with a given attribute. When a new example is given, the subject simply adds the response strength for all the attributes present in the new example. Right, during concept learning, the subject forms a response hierarchy for each attribute in the problem by tallying the number of times each category response has been or has not been associated with a given attribute. Right, so each attribute or feature, for example, if again using the red triangle problem, if they fail first time, second time, third time, fourth time, fifth time, sixth time in a row, let's take that as a benchmark, then the tally of five equates to this doesn't work. What's the other next possibility, right? And then based on the success rate forward from the right decision and identifying the correct attribute, and of course, from identification, you're now associating you are now formulating the rule, right? That concretizes which choice to now make, right? I.e., the decision to be made, which one is above the other. So, this is where you have response hierarchies. When a new example is given, the subject simply adds the response strength for all the attributes present in the new example. So, again, going back to the red triangle example, response strengths would be again positioning, shape, right? All the dimensions that exist and the features that exist. So, it's very important to make that. It's very important to be clear about that. For example, consider situation 4.1 in which subjects are shown cars with drawings that are either red or green in color, right? Large or small, round in size, round or square in shape, and one or two in number. The continuity theory assumes that each type of color, size, number, and shape builds its own response hierarchy, with the response either yes or no, based on past experience, as shown in box 4.2. So, box 4.2 is here. For example, suppose that the subject has just been shown the first six objects described in box 4.1. So the first six objects are what? One red large square, one green large square, two red small squares, two red large circles, then one green large circle, then one red small circle. Okay. The continuity theory assumes that each type of color, size, number, and shape builds its own response hierarchy. For example, suppose that the subject has just been shown the first six objects described in Form 1 must determine whether one green small square is yes or no. So one green small square is yes or no, right? So here it says yes. But how is this determined? Box 42, the response hierarchy for green favors a no response since it's been associated with no many times and few times with yes. Similarly, the hierarchy for one favors no. The hierarchy for small is strongly yes. And there is equal preference for yes and no for square. Individual tendencies for one green small square and square add or subtract to yield a weak yes response shown in 4-2. Let me simplify what's going on here. So they present these set of instances here, right? And you have to label them yes or no. Yes or no based on the card that you're given. So it's a guess. You have to guess, right? So the continuity theory suggests that subjects keep a tally of the number of times each attribute, red, circle, and so on, has been associated or not associated with yes or no. For the first few instances, the tally could be as follows. So one large square is in the no group, okay? And because it's a negative, and then 2 is therefore the opposite, it's positive. Then you have red, which is negative, and that's positive. So positive, negative, 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 large and small, negative again, positive, negative is negative again. So all of this, Richard Meyer is saying that all of this goes down to no, because the negatives outweigh the positive here. Let's look at a yes. So we have two red small squares, similar to the example I gave about triangles. Minus plus. So 2 is a positive, red is a positive, okay, and small is a positive, and square is a positive. So that goes in the yes. So there seems to be a split in the categories here, right? Because we have two yeses and one, two, three, four nos. Okay. Now, to determine the response hierarchy for each new instance, the tendency to say yes or no for each attribute must be added up for all previous instances. For example, after the first three instances, the response tendency for the fourth instance are here. Just a side note, in our dissertation, when it came to the Wisconsin class sorting test, we looked at we looked at three distinct instances where after a set of six cards presented, what's the success to failure ratio? Then we looked at the 15 card. Then we looked at a 15 card set. Then we looked at the 32 card set. So in each of those three instances, we had to determine where there's a drop in error. Is it because the participant forgot the rule? Is it they decided to switch the rule? Is there confusion because their attention drifted here and there, so on and so forth? So this is what they're stating here is after the three instances, so they've taken three here as a benchmark, and now they're going to explain the hierarchy in a moment. So when it comes to number two, it has one, two, three, four. Two has three yeses. So two, three, four. One, two, three, four. For example, to determine the response hierarchy, the tendency to say yes or no for each attribute must add up for all previous instances. For example, after each three instances, the response tendencies for the fourth instance are two, three. So two, three yeses or no, zero no's. Red is two yeses. Two, three. This doesn't make any sense. How is it two, three yeses? I know what to do. making no sense. I think the only solution is to take a picture of this. Okay, this doesn't make any sense. Okay, let's see what comes up. Okay, so let's see what ChatGPT states here. Okay. Problem is the book jumps directly into the experiment without explaining what you are supposed to be doing. What is the experiment actually trying to study? The experiment is not about shapes, it's about how your mind discovers hidden rule. Imagine I secretly invent a rule. Every object that is small belongs to yes, everything else belongs to no. I do not tell you this. Instead, I show you one card at a time. Your job is to simply answer, does this belong in yes or no? After every guess, I tell you whether you were correct. Gradually, you try to figure out the hidden rule. That process of discovering the rule is called concept learning or rule induction. What information does each card contain? Each card has four characteristics, dimensions. The book calls them dimensions. They are dimensions and possible values. So number could be one or two, color could be red or green, size large, small, shape is circle or square. So every object is simply a combination of these. For example, one red large square, meaning number is one, color is red, the size is large, and the shape is square. Nothing more. So what is box 41? Simply a list of examples presented to a participant. Participant does not know the rule. For each line they do this. For example, card 1. One red large square. Participant thinks maybe yes. Then they uncover the answer and it's no. Next card is one green large square. And then the guess is no, because there seems to be continuity. Seems to be continuity here. Right. Next card is two red small squares. So that's a yes. So is it because two or is it because they're small? Now this continues through all 16 examples. Let's solve for one ourselves. No. Yes, could this be the rule? Maybe yes, maybe red. No, because the first card is red, but no. Two objects could be third card as two, maybe small, could be third card small, maybe squares. No, because first card is square, but no. Your brain naturally starts forming hypotheses. This is exactly what the chapter calls hypothesis testing. Your brain is constantly says maybe the rule is size. So this is your brain trying to determine what the rule is. So this is rule induction, right? And trying to grasp concept formation from this point. Okay, then test it. In another example, breaks it, throw hypothesis away. So constantly testing, thinking is hypothesis testing in one of the claims here. This is exactly why the chapter is titled Thinking Analysis. Now, what is the actual hidden rule? Let's inspect all the answers. So it gives a whole list of them. Now look at only size. Large is no. So all larges are no. Small is yes. So everything small is in the yes category. Everything large is in the no category. The participant is never told this, they discover it. So why is box 4.2 needed? Because psychologists has two different theories about how people discover this rule. And box 4.2 where we are stuck, okay, illustrates the continuity theory. So instead, they keep little mental scores like this. Suppose you've only seen three cards. Okay, one card is large. Okay, so card one is large. No, your brain stores large is a no, +1. Okay, card large. Card two is large. No, brain updates large is no, which is no again. Green is also no. Square is no again, and so on. Right. So this is number two instance. Card number three is small. So this is yes. Why? Because small, as we've determined, is yes throughout. So the brain updates this, stating that yes is small, two is yes, square is yes, and red is yes. Whereas in the large square cases, they were an automatic no. So this is now category classification going on. Eventually, your memory looks like this. Okay, it gives a whole list. Okay, yeah, perfect. Notice something, only large or small strongly predicted the answer. So the only attribute or dimension that's predicting yes or no is the size of the card, of the object of the card. sorry, of the object shown on the card. That's the only determining factor at the moment. Everything else is almost about equal. According to continuity theory, you never consciously think maybe size is a rule. Instead, the mental association simply becomes strong over time. So, what are the plus minus signs in box 4.2? This is the part everyone finds confusing. The table records whether each attribute supports a yes or a no. Suppose, for example, one red large square, which is the first option here. Answer is no. So that means the one is a negative, and then red is a negative because it's a large card, and obviously is negative. And then the shape is a square. It is negative because those attributes appeared in a no example. Okay. Next card, you have two red small squares. This is a yes because it's two, which is a positive. Then you have red, which is positive. So now we're understanding the rule here. And then size is small, which is positive, and the shape is square. So overall, that's in the yes group. Okay. By the way, this is similar to how ethnic cleansing is conducted during scum rail operations. FYI, they use a similar model. I'm convinced. Then attribute everything else. Now red has one positive, one negative, meaning red predicts nothing. So red is not the predicting factor here. Small has only positives. Plus, 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 plus. Large has negative, 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 negative. Now size starts becoming informative of the object. Okay. Step 10. Why do they add everything together? Well, imagine a new object appears. For example, two green small circles, which is not written here, but this is the ChatGPT example. Continuity theory says look up each attribute separately. Attribute current tendency number 2. Yes. Green, neutral. Small, yes. Circle, neutral. Because circle has three positives, three negatives, and green has one, two, three, four negatives and two positives. Okay. Overall, probability is yes. No hypothesis, no reasoning, just accumulated associations. Second theory on page 84. The author contrasts this with hypothesis testing theory. Instead of keeping score, people think like scientists. For example, after only three cards, you might think, I bet the rule is small. Next card is large, and the answer is no. Hypothesis survive. Next card small. Answer yes, still survive. Eventually, you conclude the rule is size. This theory says people think consciously in terms of rules. Tie chapter in one picture. I like this. Hidden rule, participants use example, large, large, no, small, yes, large, no, small, yes. How does the mind learn? Theory 1, continuity. Keep association scores, small, yes, large, no. Theory 2, hypothesis testing. Guess a rule, test, reject, or keep it. So the key takeaway, box 4.1 is not to test your knowledge of shape colors. It simulates the experience of discovering an unknown classification rule from feedback. The purpose of box 4.2 is to show one possible explanation of how the mind might accomplish that task by gradually accumulating association between attributes and the category yes or no. The rest of the chapter argues that humans often behave more like scientists forming and testing hypotheses than like simple association count. Hmm, that makes sense. I like this. I'm actually going to make this into a note. Stuff and it here. I like how ChatGPT explained this as a seasoned professor. And let me make this into a note. Okay. Okay. Yep, in ethology, we have the classificatory system that exists as well. There. Large, no. Small, yes. So that's number one. Number two, we shall put here in a second. Number one, number two, here. Okay, is the mic does the specific continuity. Keep association scores small is yes, then large is no. So these are the determining features here. Okay, so nice breakdown. Theory 2 is hypothesis testing. Okay, theory number 2 we have here. Actually, it's time for market, so I have to go soon. Inshallah, we will touch on the rest soon, very shortly. Tomorrow, actually, hypotheses. testing. Okay, so that is guess rule. Yep, and then test it. Reject will keep it. Reject will keep it. Okay, nice and simple. Okay. So we've done this. I guess we can read the brief for Hall's paper. Let's see this one here. So, six of the Chinese radicals that Hull used are shown here. First, the subject was shown a Chinese character and guessed its name. For example, Wu. Then the experimenter gave the correct name and so on. Characters with the same radicals always were given the same name, so that after going through several packs of characters, the subject improved their performance and were eventually able to correctly name characters they had never seen before. So, this is again a task of concept learning, concept formation, understanding the rule of induction. So let's read the summary here of Hull's work first and foremost. So Hull's classic 1920 monograph, Quantitative Aspects of the Evolution of Concepts and Experimental Study, represents the foundational pivot in early cognitive and behavioral psychology, inspired by Hermann Ebbinghaus' quantitative work on memory. Hull's aim was to move concept formation out of the realm of vague, subjective introspection and into rigorous, measurable lab testing. To achieve this, he devised an ingenious methodology using unfamiliar Chinese characters as visual stimuli. Embedded within these complex characters were specific recurring radicals of concept. Participants were shown the characters and tasked with associating them with designated nonsense syllables, the concept names, by systematically manipulating variables such as the order of presentation, simple to complex versus random. Frequency of exposure and structural complexity of the surrounding character whole track the precise mathematical trajectory of how human mind isolates an abstract rule from concrete examples. Main finding of the study demonstrated that concept formation operates as a gradual incremental trial and error process regulated by associative mechanism, closely mirroring Thorndike's law of effect and exercise, like in the cat study. Hull observed that participants could successfully identify and categorize new characters long before they were consciously aware of or able to explicitly draw the hidden radical. This revealed that abstraction often occurs implicitly through generalized habit formation rather than sudden flashes of conscious insight. However, looking at this through a modern lens, the study has notable functions. Because Hull was operating at the dawn of behaviorism, his framework treats concept evolution purely as passive accumulation of statistical regularities and identical elements. This entirely overlooks top down semantic processing, cognitive schema, and active hypothesis testing. Furthermore, the lab tasks were highly artificial, pairing nonsense syllables with foreign orthography lacks ecological validity and fails to capture how rich abstract human concepts like justice, danger, and democracy develop in real world culture and linguistic contexts. Hmm, interesting. So, tomorrow we're going to do a political essay. Sorry, look at Cyrus's political essay, and possibly on the same day, if not on Monday, we will continue to look at Hull's work here, inshallah. Okay, till then. Assalamu alaikum wa rahmatullahi wa barakatuh.